Welcome back to CF 712. In this session, I'm going to talk about regular grammars. So a grammar is regular if each production takes one of the following forms, where uppercase letters are non-terminals and W is a non-empty string of terminals. So one possibility is that a non-terminal goes to nothing, lambda, the empty string, or a non-terminal might go to a string of terminal symbols, or the non-terminal goes to another non-terminal, just a renaming rule, or finally, non-terminal goes to a string of terminal symbols followed by a terminal symbol. Sorry. Let me try again. The non-terminal goes to a string of terminal symbols followed by another non-terminal. So basically, only one non-terminal can appear on the right-hand side of a production, and it must appear at the right end of the right-hand side. If you have those restrictions, then the grammar is called regular. Based upon the name, you probably have guessed what's going on here. In fact, regular grammars generate exactly the set of regular languages. And we can do this proof again by construction. Given a regular grammar, I can generate an NFA for it. So given a regular grammar that generates a language, I can construct an NFA to recognize that language. And then the reverse is true too. You give me an NFA, and I'll give you the regular grammar that will generate the language recognized by the NFA. And the key idea here is that non-terminals in the grammar are modeled by states in the NFA, and vice versa. So we'll just look at some examples here to get the idea of how this works. Let's start with a regular grammar on the left, and we can immediately write down the NFA for that. So this production S goes to AS. All I do is I just model the non-terminal with a state. I'm assuming S is the start symbol, so it's actually the initial state of the FS of the DFA. It's actually an NFA. Okay. And then I model the production S goes to AS as just a self loop, right? I consume an A and stay in the same state. Similarly, S goes to BI. That's a transition to another state called I because of the other non-terminal. Okay. I goes to A. That's actually a transition to the final state. Because if you think about it, and we'll do a derivation on another example in just a moment, if you think about it, there's only one non-terminal alive at a time. If we think about this as a derivation, a grammar derivation, I start with the start symbol, I go to AS. S might go to I. I goes to itself. So we never introduce more than one non-terminal into the derivation. So when I choose to take a non-terminal to a terminal symbol or a string of terminal symbols and I don't introduce a non-terminal, that's got to be the final step in the derivation. Okay. So again, I model the I goes to A as a transition to a final state. And finally, just to finish up this grammar, this one is a self loop again. I goes to itself, consuming an A along the way. So basically, you give me the production, I can write a piece of the NFA. Okay. I guess maybe a more coherent way to think about the construction is first of all I create a state for every non-terminal. I create a state for the final state, and then for every production it's put an arc in between these states. Okay, and this start symbol, the state for the start symbol is the initial state. Let's look at another one. This example just introduces some strings of non-terminals, strings of terminal symbols. So if I had a grammar like this, S goes to AS or S goes to ABA, I, all I'm going to do is I'm going to, the S goes to AS, that's easy, right? A self loop. Again, S is assumed to be the start symbol, so we make it a initial state. And then the ABA, I just model that with a series of transitions between states. So I introduce these extra states that are not don't correspond to non-terminals just in order to match that string ABA. And that puts me in a new state I, and then I can go BAB, and again, because I don't introduce a non-terminal on the right end here, it's got to lead to a final state. Okay, and finally I have the fourth production, which is just a self loop on I consuming an A. So again, you give me the grammar, I can construct the NFA in a very straightforward manner. Okay, what about the reverse? What about the reverse? You give me an NFA, so you give me an NFA here. And again, basically I'm going to introduce a grammar symbol for every state. So I'm going to introduce productions for S, productions for I, productions for K, and productions for J. The initial state, its non-terminal becomes the start symbol over here. Okay, and then I model each transition with a production. So S goes to AI, S goes to AI. Notice the lambda transition here, S goes to J. There's just S goes to J. It's just a renaming rule. Lambda doesn't consume any input. Okay. I goes to K on the B arc. I goes to BK. J goes to itself, JAJ. J goes to K, consuming an A, JAK. I have a self loop on K. K goes to AK. And then the key point here is that how do I model the fact that K is a final state? I just null derive it. So I reach state K, I can stop the derivation, I can stop the recognition of an input string by just going to K goes to lambda. Okay. So model the final state with a null rule. So here's a derivation down here for the string ABA. Let's just watch how it works here. So again, if we go back to the original machine, A, B, A. Yes, that's in the language. So the parser ought to be able to do a derivation. Start with a start symbol. I write S as AI. Notice I only have one non-terminal at each step of the way. So I don't have a lot of choices to make here. I got to remodel, I've got to then rewrite I to be BK, so ABK. I'm going to have to rewrite the K. And in this case, I want to introduce that last A. So I go KAK. And now I want to model the fact that I'm done parsing. So I null derive K. Okay. So again, you give me an NFA, I can give you a regular grammar. So back to the theorem, I can go in both directions, right? Regular grammars generate languages that we can match with an NFA, so they generate regular languages. But the question is it a subset? Well, no, it's not, because you give me an NFA, I can give you the regular grammar. So any regular language I can match with a regular grammar. So it's an exact match. NFAs and regular grammars have the exact same power, and in fact we know since NFAs are the same power as DFAs, DFAs and regular grammars have the same power. Okay, so that's just a little bit of a lead-in into the world of grammars, which is really the next thing we're going to tackle in the theory part of the course is to go to context-free grammars and, gee, what machinery do we need to recognize those? Let's stop here.